Hello everyone. Today we are going to talk about balanced three-phase circuits. What are the balanced three-phase circuits? Well, due to economic and operational advantages, the electric energy is generated and distributed in three-phase form rather than a single phase. For example, this one is the generator, which has a sixth terminal, and it is generating AC signal. The prime terminals, A prime, B prime, and C prime, they are all connected to each other. So they will have the same potential. Like this. So we can consider this is the generator. And this A prime and B prime and C prime, they are all connected to each other. So we can call that A prime, B prime, and C prime node N, or neutral. Now, VA A prime will be a signal which is generated, and it will have some magnitude Vm with some sinusoid cosine and with a frequency omega times t. Okay, let's consider that in this case we don't have any phase. In the simplest form, VB prime will be in the same form as the VA prime, but this time this will have a phase difference minus 120 degrees. So this means that we will go 120 degrees in the clockwise direction, and to get VCC prime, we will go another 120 degrees in the clockwise direction. Or we can say we can go 120 degrees counterclockwise from VAA prime to VCC prime. Okay, they are the same. These are called our generator will have three phases. Okay, if we choose this phase, I mean this generator, this part, this will be our reference, and with respect to this VAA prime, we will go 120 degrees each time in order in the clockwise direction. So from VAA prime it will be minus 120 degrees, which will be 120 degrees clockwise, and again 120 degrees clockwise from VBB prime to VCC prime. Or we can go from VAA prime to VCC prime plus 120 degrees in the counterclockwise direction, which they are the same. Okay? Now, I want to take your attention to the fact that we can also show this in the phasor diagram. Now, we have a phasor diagram like this, and one of them, let's consider it as a reference, which is VAA prime. So these are VAA prime, and this is also for in the real, and this is in the imaginary. So if we go clockwise 120 degrees, it will be approximately this one. So this is 120 degrees, and If we go another 120 degrees, it will be something like this. This is VCC prime. Or we can go counterclockwise 120 degrees from this one. Okay. Now, please note that VAA prime plus VBB prime plus VCC prime will be equal to 0. Because if you add these vectors, their addition will be equal to 0. Okay? So that's why we will say they're balanced sets. Or we can this is also corresponds to KVL. Okay? They're balanced. Now, in the Y connection, which means our generator is in the form of Y. So this will be our schematic, this one. So we can say B prime, C prime, and A prime, they are in the node N. Okay, now, what do I mean by saying that? Well, let's say this is our node N, and this part is our generator. And this is node C. These are little letters, B. So in the source side, in the generator side, they will be little. And these are going to connect to our loads. Now, this is node N, so this plus minus, this voltage difference will be VAN, which is VAA prime. Okay. This is also VBN, which is VBB prime. And this is also plus minus VCN, which is equal to VCC prime. We also have line to line voltage or line voltages like this one. These are between these. So this will be V of BC, okay, which is line to line voltage, or this one to this, which will be VAB, or we can say this line and this line, which will be VCA prime. It's VCA, sorry. Okay. Now, what do we know about this three-phase connected generator when the generator is balanced? What is VAN, and what can we do? How can we find VAB, VBC, and VCA? So, let's say VAN is equal to VM with 0 phase. So we picked, which is this one, right? We picked it and it doesn't have any phase. So accordingly, VBN should be VM with minus 120 degrees phase, and VCN should be VM with plus 120 or minus 240, we can say. Now, how can we find VAB, VBC, and VCA? How can we find these? Well, VAB is what? Is VAN minus VBN. right? So if you go and you can find it algebraically very easily, and then you will end up getting radical free Vm with phase 30 degrees. If you found one of them, like VAB, again, we can go clockwise 120 degrees each turn, and we will find other VBC and VCA as well. So it will be, this one will be radical free Vm. If we go 120 degrees, what will it will be minus, so this will go minus 120, so it will be minus 990. This will be the same. So their magnitude, as you can see, is equal, but their phases are different. So this will be, if we go minus 120, it will be minus 210, or we can say 150 degrees from this one to this one, plus 120 degrees. Okay. So so how did we find this? I said that if you go algebraically, you will get this one. But other way to get it, which is very simpler, is to go with phasor diagram. So if this is our phasor diagram, this is real and this is imaginary. This is VAN. This will be VBN. And this will be VCN. What will be VAB? Well, VAB is VAN minus VBN. So minus VBN is this. This is minus VBN. So if we add this and this, what will we get? Okay. Now, since this is 120 degrees, this part will be 60 degrees, right? So VAN will be their summation, and this part is 30 degrees and this part is 30 degrees. So the contribution of those from from minus VBN, it will be radical 2 over 2, radical 3 over 2, and from VAN it will be again radical 3 over 2. So the overall will be radical 3, or square root of 3, times their magnitude. So if VAN has a magnitude of Vm, okay, then this will be radical 3 Vm. I'm not going to write them, but you know this, okay? This will be radical 3 of Vm. I'm just writing their magnitude. And the phase difference, here you can see it is plus 30 degrees, as it is shown here. And if we go minus 120 degrees, then we can find the other ones. So if we go minus 120 degrees, this will be our VBC. As you can see, it has minus 90 degrees. And if we go another minus 120 degrees, this will be our VCA. You got the idea, right? Okay. Now, So what we notice is that V line magnitude wise will be equal to radical 3 times V of phases. Now, I want to show you another thing, and that is Y to Y circuit. Y to Y circuit. Let's bring it down here. I have already sketched it. So here you can see this part is our source, which we had in this section. This is the generator side. So we had this part. So this is our generator or source side. And now let's consider when we have our load is also in the form of Y. So our source is in the Y form and our load is also in the Y form as well. So consider this is a generator outside the city, and with those transmission lines, we're connecting it to the load, which is, for example, city or a factory or customer. And the factory is also in the form of Y connection, Y form. So since there is a lot of distance between the generator and the load, we will have impedance in the transmission lines, as you can see here. So impedance won't be negligible because the distance is very 100 kilometers. So as you can see, we represented the source side with little letters A, B, and C. And this is also the source V, A, and we talked about them. And when we have in the load side, we have also ZB, ZA, and ZC, and they are all, their impedance all equal to each other. So that's why we will say these are balanced, because everything is symmetric. You can see VBN, VAN, VCN in terms of magnitude, they will be equal to each other, and these also, their impedance will be equal to each other as well. So VA, IA will go and will be equal to this one. They will be the same as well. Also, the transmission lines ZL will be also the same. Because from the source to the load, these distances will be the same. Okay. And this N, which is connected here and here, we can call them a neutral node. And there won't, if you connect with a wire, this part to this part, there won't be any current going flow that node to that node, because they're in the same potential. So their potential difference is 0. So we won't have any current going through that. And to prove it, you need to go through superposition. You need to kill, for example, if you want to know, you need to kill this one and this source, and you just consider this source. And then we will have a current I, for example, like this, passing through. And this I will have some phase. And if you kill this source and keep this one, it will have another I let's say I prime. And if we continue like this, and if we sum them up, their magnitudes are equal, but since their phases are 120 degrees, 120 degrees, and 120 degrees are different from each other, if you add them, you will get a zero current. That's why this current is there is no potential difference between these two nodes N. Okay. Now let's talk about how can we analyze this kind of circuit. In order to be able to analyze this circuit much efficiently and better, we can analyze per phase circuit. So we can divide this complex problem into pieces to get a better idea and to analyze it better and better. So let's go for per phase circuit. In per phase circuits, I will just consider I have just VAN and just one transmission line and just one load. Okay, so I will consider this scenario. This is grounded, which is, we can call it node N also, or neutral node. And it is connected to VAN. And in the source side, we said it will be little symbol. We will use A, little a. And then we will have transmission line impedance, ZL. And we will connect it to node A. And this is our load. And connect it to the ground again, which is node N. As you can see, this is connected to load N. This is also connected to the load N. So there is no difference. This will be VAN. On the load side, we will use capital letters. On the source side, little lower letters. So this will be IA, which will be equal to, you can say I in Y to Y connection. Now, recall that VAN, VBN, and VCN are balanced. Are balanced set. Now, what is IA? What is this? Well, this is, with using the Ohm's law, you can say the difference potential over the impedance, right? So this will be VAN over ZL plus this ZL, which is this one, the load impedance. This will have a magnitude, let's call it IL, with some phase, let's call it theta. And VAN, what is this? What is VAN? Well, VAN with Ohm's law, we can find IA times ZL, which will have, again, VL magnitude with some phase, like alpha. We can find IB, IC as well, or VBN and VCN as well. So IB will be, it will have the same magnitude, but minus 120 degrees. and VBN also will have the same magnitude, but with 100 minus 120 degrees in the clockwise direction. And likewise, IC will be IL theta. So if we go another 120 degrees in the minus side, or we can go plus 120 degrees. And this is VCN. Plus 120 degrees for simplicity. Now, if we add these IA, IB, IA, IB, and IC, we will get 0. And if we add these two, VAN, VBN, and VCN, we will also get 0. So that's why it is called balanced. Okay. Now, this is very, very, very good, simple. So if you find just one of these sets, if you find just these two, you can go to find another sets easily by just adding the phases 120 degrees each turn. Okay. Now let's consider complex power delivered to these loads in each phase. Okay, let me get this one again. Okay, what is complex power? Well, complex power formula, we had IRMS to power 2 times the impedance, right? This will, one of the formulas, this will give us a complex power. So SA, the complex power for the load, for the A, will be, for the load A, this is load A, right? Will be IA RMS value, its RMS or effective value, to power 2 times ZL, which is the impedance. So this is called per phase complex power. So we're considering just for one phase. We have 3 phases, right? So this is for one phase. Now, since the magnitude, so we know this is just a magnitude, right? Since the magnitude of these guys are equal to each other, so their complex power as well will be the same. So SA equal to SB equal to SC, because this is a completely symmetric and balanced circuit. We're talking about it. Okay, now, how about they gave us, they want the total, for example, complex power from us, or they want how we can go from a per phase power to the total one. Well, we know, let's say for current in the per phase, we say IP, and the voltage per phase, let's say this is VP, which is, this VP is across this one. This is a VA, okay? VAN, for example. Now, so this is IP RMS, then it will be equal to, for example, IA RMS. And this is also RMS value will be equal to VAN RMS value. Okay, so this is called RMS per phase. So this is called RMS per phase current, and this is called RMS phase voltage. Okay, now let me draw a table. Let's say we have this one. Okay. Let's say this is per phase and this is total. This is complex power. This is real power or average power. This is reactive power. Or let me write it like this. Reactive power. And we also had apparent power. Now, complex power, we found it per phase will be equal to IP RMS square times the load, ZL. Then the total complex power, okay, let me tell you. Per phase, the complex power of each of these, like as I said, we showed here, SA, SB, and SC, they're equal. So due to the conservation of the power, it will be their summation. So it will be 3 times of one of these. Okay, so complex power of 3 phase will be 3 times one of the complex power of one of the phases. This is per phase. And for the real power, what was the real power? It was IP RMS square times real part of the ZL. Okay, and this is also equal to 3 real power per phase. This was QP IP RMS square times imaginary part of the load impedance, which will be Q3 phase 5, which is, it means 3 phase, equal to 3 QP. And the apparent power, which is the magnitude of the complex power, which will be equal to IP RMS times the magnitude of the impedance, or we can simply say IP RMS times VP RMS, right? Which will be equal to the apparent power of 3 phase will be equal to 3 times one of the apparent power of each phase. So this is very important. Or you can also say another formula to find, for example, this one, we knew that it was what was the formula? It was V PRMS squared over real part of the Z conjugate. You can find as well this one as well. The same for this one. So this will be QP. I'm writing just another form of formulas. imaginary part of the z conjugate. Okay, and etc. All right, this was a brief talking about the three phases, and it was quite nice and very, very good to know these concepts. Also, we have I'm going to solve some examples about this part, y to y, and also I will have a delta connection as well video. You can watch them. And thanks for watching.